Here we go. So we're in section 12.1, right? So this is the classification of finitely generated modules over R equal to a principal ideal domain. So I'll get straight to it. This is Theorem 5, which is the fundamental theorem on existence, and it's the invariant factor form. So there are two popular forms. The one is the invariant factor form, the other one is the elementary divisor form. All right, so we'll start with this one. And so let R be a PID, and M finitely generated R module. Then number one, M is isomorphic to the Cartesian product of R with itself R full times, direct sum with R mod an ideal generated by A1, direct sum R mod an ideal generated by A2, direct sum R mod the ideal generated by A sub M. All right, for some R greater than or equal to 0 in an integer, and non-zero A1, A2, AM in R, which are not units, and what else do we know about these guys? They satisfy divisibility relations. A1 divides A2, and so forth and so on, until finally, AM minus 1, and then that divides AM. All right. So these satisfy divisibility relations. All right. Number two, M is torsion free. If and only if M is free. By the way, M being free means that M is just isomorphic to R to the R. Okay. And three, what is the torsion of M? Well, tor of M is isomorphic to the piece that's not the R sub R term, right? So the R mod A1, direct sum R mod A2, like that. So, excuse me, definition. The integer R theorem is the free rank. The free rank or Betti number of M, right? And A1, A2, AM are the invariant factors of M. All right. However, since every PID, remember, is a UFD, right? It's been a minute since we talked about that, hasn't it?
Yeah, unique factorization.
So our PID implies R is a unique factorization domain, which means that each one of these invariant factors has a prime power decomposition, right? And so, like, for each A above, each A can be written as, some unit times P1 to the alpha 1, P2 to the alpha 2, PS to the alpha S, right? And if you allow these powers, if you allow the powers to be possibly 0, right? Then you could let P1 through PS be the distinct list of primes that appears in the totality of the list A1 through AM. It's a trick I just learned in my current online number theory. I don't know why I know this before, but it's like such an obvious idea for notation. If you just allow these to be 0, then it can be 1, right? So like if each one of these happened to be a prime, you could just like put alpha 1 equal to 1 and the rest of them 0, and S would be equal to M in that case, But generally it's more complicated than that. But the point is that because of that, that gives you Theorem 6, which is the elementary divisor form. Which says basically that M is isomorphic to its free piece, R to the R, direct sum with R mod P1 to the alpha 1, the ideal generated by that, R mod P2 to the alpha 2, direct sum R mod P sub T to the alpha T, the ideal generated by that, right? And here, definition, right? These guys, these are the elementary divisors of M. All right. So the claim is essentially that you can classify a given R module either by giving its free rank and a list of invariant factors that have to satisfy these divisibility conditions, or you could classify M by giving its free rank and a list of elementary divisors, right? And of course, the elementary divisors a little bit trickier because these could be written in any old which way, Like the direct sum decomposition is commutative in that sense. In contrast, over here, there's more of a uniqueness built into this because you have this assumption of divisibility of the invariant factors. See? So I think partly for that reason, as you look at different books, you'll find kind of different versions of this as you see it put into practice. Like if you compare the rational canonical form in one linear algebra book to another, you might find a little bit of a difference. At least I have. When I compared, say, Curtis's linear algebra to, I think, Dummett and Foote, it's a little bit different. But anyway.
Are you talking about a particular theorem in the definition agreement?
The theorem?
Yeah, the integer r.
Theorem 5.
Okay.
Theorem 5.
I thought you were.
Yep. And then finally you could, there's yet another one, Theorem 7, the primary decomposition theorem. So Theorem 7 is the primary decomposition theorem. So here, these primes, oh, my bad. So I was saying that these were distinct primes, right? But that's not the case, actually, for Theorem 6. Those don't have to be distinct primes. These could be, they could be repeated. Okay. But that's okay. I could still have a list of primes possibly repeated that take the alphas to be, anyway. Sorry. But the primary decomposition is that you have M isomorphic to, again, the free part, direct sum with like n1, n2, however many of those. Let me see his label. This is all from Dummett and Foote. This is Theorem 7, I believe, in section 12.1, I think, and n sub n. And n sub n. And here, n sub I is the p sub I primary component. It's, let's see if I can be more careful. N sub I is, let me just give a definition right here. N sub I is equal to, it's kind of like an annihilator, all right? X and M, I mean, I think it is an annihilator, actually. X and M, such that pi alpha to the I, x equals to 0. And I believe here the, allowing alpha to be whatever power, and, oh, excuse me, my bad. My bad. What is alpha? The pi and alpha I is significant. I should mention M has non-zero annihilator. The torsion has non-zero annihilator A. So here A equals to U1, P1 to the alpha 1, Pi to the alpha I, and so forth. Pn to the alpha n. This guy, all right, is the annihilator of the module. All right. Well, it's n sub I is n sub I has annihilator pi alpha to the I, and it's a submodule of M. And here, this list, my bad. I mean, it's unfortunate notation, right? Maybe I should put like a p tilde over there or something. These are not the same list of p's necessarily. These are distinct, okay? So primary decomposition, it's breaking it up into distinct prime pieces in some sense, like that. All right? I have some examples. So major applications of this for us is, first and foremost, perhaps, the fundamental theorem of finitely abelian groups is this business for, I should say it this way. This reduces to the classification theorem of the fundamental theorem of finite abelian groups in that case. It also gives us various ways to break down a vector space You remember that module we built over the polynomial ring? The fx module of v based on the linear transformation t from v to v. So that's, when we apply these theorems to that, it's going to give us the canonical forms of the linear transformations. So those are two major applications. The other application is if we're just given a list of like relations that have to be satisfied of integer coefficient equations, that defines some kind of module, and there we're also going to use this theorem to kind of understand those kind of systems. Those kind of systems we'll see come from like the problem of there's something we can do. There's some kind of group, abelian group that you can build. I'm thinking for a knot. I think I have that as an example I can show you. But anyway, so sorry I had to erase this. Hopefully that won't be too bad. It would have been better if I didn't have to erase it. I know, but TikTok, you know. Who keeps calling me? Missed call. What's that about? I'll call him back in a minute. Let's see here. I have had weird random calls today. So here's just, this will be it for today because our time is limited, as you know. But so here's an example. Various finite abelian groups, order 1800. Now 1800 is 2, let's see here, what is it? I say 2 cubed, is that right? 2 cubed times 3 squared times 5 squared. See if I believe that or not.
25 times 27 times 8.
Yeah.
25 times 27 times 8. 5,400. I think you're 3 off. You gotta take a 3. You gotta take a squared off of 3.
This is just 2 squared?
No, it's 3. It's 3. Yeah. Take the square off of 3.
No, I think that's okay. Actually, this is okay because 4 times 25 is 100. So these two guys give me 200, and then 200 times 9 is 1800. It's okay. It's okay. So I have elementary divisor form. And I have invariant factor form. All right. So one thing we could have would be like, I say Z8 cross C, and maybe I should, let me just take an extra step here to write this as Z mod 8, right? Z mod 9. Let me write that 8 as, good grief, I'll get it eventually here. 2 cubed, yeah? 3 squared. All right. Z mod 5 squared.
Are these actually different from Z mod 5?
Now, no, this is,
Okay.
this, so let me put it back in the usual notation. So this is Z8 cross Z9 cross Z25. Okay. Elementary divisor form. There's no divisibility between these, yeah? And then the invariant factor form here is kind of silly. It's just this. So that's Z, you know. Well, I mean, you could write it this way, 1800Z, right? But in the notation of the theorems we were looking at, that's this. It's the ideal generated by 1800 with respect to the ring of integers. All right, so all of this is our PID is the integers, okay? That's the principal ideal domain with which we're dealing with here. Now, that's case 1. Not that interesting, right? Case 2, you could have, and I'm just going to stick with this notation because it's quicker, right? Z8 cross Z9 cross Z5 cross Z5. All right. And in this case, the elementary divisor form is, let's see here. I think, let me try to fix, my notes have got it backwards. I should put Z5 and then 360, Z5, Z60, right? 360.
So you can just mix match these?
Well, these are isomorphic.
Yeah.
Now, so like here, this has got A1, this has A1 equal to 5, A2 equal to 360, right? Mm-hmm. As you can see, 5 divides 360, okay? Also, I would point out that the primary decomposition of this one, and this is N1, this is N2, this is N3. Those are the pieces that correspond to prime 2, prime 3, prime 5. Here, the primary decomposition is just a matter of separating these pieces. Like, here's the piece from prime 2. Here's the piece from prime 3. Now, the piece from prime 5 is actually this cross this. That, speaking of the primary decomposition.
Isn't that like our way of like saying, remember how if we had like z to the 2 power,
yeah,
you could say z cross z or z4 cross z2, or, you know, is this not somewhat related?
Well, these are different though. Like, I mean, what I'm trying to say is Z2 cross Z4 and Z2 cross Z2 are different, right?
Yeah.
Yeah. But if it is a thing of order 4, it either has to be Z4 or Z2 cross Z2. Yeah, I mean, that's true, right? Z8 cross, let me keep track here. So next I have Z8 cross Z3 cross Z3 cross 25. And over here, correspondingly, we have Z3 cross Z600. This one has A1 equals to 3 and A2 equal to 600. As you can see, the divisibility, right. Okay. So this one has a different, but you see the primary decomposition are distinct, right? Like, yeah, the same primary decomponent for the 2 prime, and this has, but in contrast, the primary components for the 3 and for the 5 are distinct here, right? This one, the 5 was, the N3 was Z5 cross Z5. Here, N3 is Z25. Whereas here, N2 was Z9, and here, N2 is Z3. They're different. You can tell the difference between non-isomorphic modules by having non-matching primary decompositions, or by having non-matching invariant vector forms, or by having non-matching elementary divisor forms, although we have to be careful to make sure we're not misjudging because we could reorder things technically.
Oh, okay, so you can say the same reason for Z4 and Z cross Z2. Z2 cross Z2 not being the same.
Yeah, I mean,
Invariant vector forms are different.
Like this, we could of course also write as Z25 cross Z8 cross Z3 cross Z3. I'm trying not to do that for the sake of conversation. There are many different ways to rewrite that without even changing anything. I mean, of course, if these are relatively prime, then we have a theorem that it's the direct product of, ZR cross ZS is isomorphic to ZRS if the R and S are relatively prime, yeah? But, so So yeah, I mean, there's all kinds of like simplifications that could be made here, but I'm trying not to do that as to illustrate the elementary divisor form. So, next up, let's see, where was I? Tell you what, I'm going to skip ahead a bit. There's a bunch of these. I'll skip ahead to Z2 cross Z2 cross Z2 cross Z9 cross Z25. Trying very hard not to write, not to miscopy like one line in the next. Let me check that. Make sure I'm on the right line here, guys. Z2. Where's my 222? 925. And then that gives us Z2 cross Z2 cross Z450. That's the invariant factor form, where here we have 2 divides 450. There's my A1, 2, and 3. And again, this would be my N1, right? This would be my N2 and my N3 in the primary decomposition way of thinking. And as you can see, they're different than, well, I mean, they're different, but like if up here, this is my N1, N2, N3, right? So yeah, they match up with N2 and N3, but N1 is quite different, right? Yeah. So this has an element of order 8, this does not.
Yeah.
But this, on the other hand, has many elements of order 2, whereas this has less elements of order 2. I mean, they're different groups.
Yeah.
So, let's see here. And I don't think it's at all obvious how you would go from, I mean, is it obvious how to go from here to here? Maybe it is, or vice versa. So to figure out the, I think it was A sub m as I called it, right? Mm-hmm. That's kind of like the, let's see, how can I say this? I think it's the element of the largest order and all this stuff. So what's the element of largest order in the first one? Like,
The element of largest order?
yeah, I mean, you see, it's just like a generator for this, a generator for that, a generator for that. Then the order of those generators are 8, 9, and 25 respectively. Mm-hmm. Those are relatively prime, so the order of a triple is then the, it's just the multiple of those orders. So that has, if I take like 1 comma, for example, if I take 1, 1, 1, mm-hmm. that has order 1800.
Yeah.
And so that tells me that there's an element of order 1800 in here, and that gets me over to here. In contrast here, the I think the element of largest order comes from 8 times 9 times 5. If you sort through it, I think that's like the biggest you can get here is 8 times 9 times 5, which is I think 360. This one, we've got a 25 element of order of element. We have a 25 order thing here, 3 order thing here, 8 order thing here. So what's 8 times 3 times 25? What's 24 times 25? Please let it be 600. Yeah. So that's why there's a 600 here. So basically you're looking like one way to get from here to there. You find the element of largest order, and then you have to go, well, I know in total there has to be an order of 1800, because we're working on a findability group of order 1800. So if this is Z360, then what has to be left over is 1800 divided by 360, which is 5. And like here, 1800 divided by 600, that has to put a 3 here. Now this is a little bit trickier because you get a
Z4?
Yeah.
No, I don't think, you can't have Z4, right? Since it's coming from that Z8. Like you couldn't split it up Z4 cross Z2.
Yeah, so I think the element of largest order here is order 2.
Yeah.
And so you get order 2, order 9, order 25. 18 times 25 is 450. But then when you divide the 450, 1800 and 450, you get 4. So that might make you think, well, I have a Z4, so it's Z4 cross Z50 before 50, but it's not that case here, because see, there's a Z2 cross Z2. There's no Z4 over here, so you can't have a Z4 over there.
Yeah.
Something like so.
Is it because the order of those of N1 doesn't have an order for the whole thing? Like N.
Yeah.
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 I can't have Z4 on the other side.
I think that's one way to look at it, but this is what we want to understand more, is like how, first of all, for a given module, how do we find the either elementary divisor form, the invariant factor form, or the primary decomposition representation of the given module? And it turns out there are a number of calculational techniques. One of the major ones that we'll learn next time is called Smith normal form. There's like it's a really neat algorithm you can do to find it for the FX module. But anyway, more about that next time. As you know, KME is upon us. So no, it's at 5. But I concur with your sentiments, as it's not math. Seems like it should be math, but it's not.